Oh, okay. No time for that. All right. So, in your book, when it starts this section, this is section 32.6, by the way, if you're looking at it. I found 32.6 to be kind of hard to read in your textbook, so I'm going to try and give you a simpler version of it today. It starts off by describing the kind of the process that we use for things. So when we were doing electricity, they like to draw lots of parallels here between electricity and magnetism. When we're doing simple electricity stuff, and when we were like the basic thing for electricity that you use when you're talking about statics is Coulomb's law. And then the basic definitions of electric field and that sort of thing. But then when you get to more complicated systems, if you have lovely symmetry, then you can use our favorite Gauss's law, right? So the point of Gauss's law is that you can do a surface integral that's really, really simple, right? It wasn't a hard thing once we got unscared of it, okay? If we have a complex system of charges with a high degree of symmetry. And whether you love it or you're a little afraid of it still, I hope that we get there before May. But it is quite a beautiful thing to be able to just state that you can take the area, right, and you just find the flux and life is good, okay? In magnetism, we have a very similar deal. I find this one to be even more straightforward, so I hope that's helpful for you. When we're dealing with trying to find magnetic fields, we've got the Biot-Savart law, right, and that's pretty nice. And just to kind of get that back in our heads, that's the one that's defined as B is equal to mu naught over 4 pi times the very basic one is Q cross R. Oops, Q is an actual, or QV, excuse me. Wow, come on, Carboling. QV, that's the vector, cross R over R squared. Okay? And this is doable. You can use this or its current equivalent to find any magnetic field you want. But we're going to look at much more complicated situations. And in some of those complicated situations that have a high degree of symmetry, we can use another law that makes our life so much easier. And that law is called Ampere's law. Okay? So Ampere's law, it's very similar. It's, you know, kind of the parallel existence to Gauss's law in that it's for complex systems of currents or moving charges with a high degree of symmetry.
What a low degree of symmetry?
So, like, a high degree of symmetry in charge distributions are like, you know, a sphere of charge that's all equally distributed. Whereas if you had something that looked like the surface of an egg on one side and a flat thing on another side, that would not have a high degree of symmetry. Does that make sense?
Or is that like not be symmetric at all?
Right. Right. So we're looking for things that have really nice symmetry, either spherical symmetry or like symmetry around at least some sort of curve that's easy to find.
So example of symmetry was like it is or it isn't, not like there are degrees of it.
When you take higher level math, you will see like there are degrees of symmetry. There are things that are very symmetrical and things that are very not symmetrical. And then there are things that like have got some symmetry that makes it a little bit more approachable, but we're not going to deal with those today.
So would this be something like if I had a charged ball and I threw it, and it was moving?
Kind of.
Okay.
So we're not even going to do things that are that hard.
Okay.
We introduced Green's law so we can evaluate surface integrals using line integrals.
No. I'm just going to say that. Say that to Gabe. No, not going to. All right, here we go.
Usually just ignore Gabe once he says, or.
Then turn off. All right. So, to be completely honest, one of the reasons that I don't like your textbook is in this. I like the textbook most of the time. I didn't really like the way that it introduced Ampere's law because it was just like, and so now let's take a dot product. It's like, why? You know, usually it explains like, and so we're going to do this. Da, 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 da. And so I was looking at a different textbook, and it kind of did that too, but it had a little footnote. And I found the footnote to be very interesting, so I wanted to share it with you because it made me feel a little less stupid when I was looking at it, right? Like, because it didn't seem obvious to me. This is what it said. And it was almost like it was being written to me. Dear Miss Carbeling, it doesn't really say that, but that's what I felt like it said. You may wonder why we would choose to evaluate this thing that I'm going to share with you in just a second. The origin of Ampere's law is in the 19th century in which a magnetic charge, the supposed analog of an isolated electric charge, so this is before we knew that you couldn't have one pole without the other, right? Okay, was imagined to be moving around in a circular field line, whatever that means. They were trying to find work done on the charge was related by this dot product, just as the work in done moving an electric charge in an electric field. So electric charge in electric field, you find the work by doing E dot ds. Yeah? We know that. That's what we did a couple chapters ago. So Ampere, in his brilliance, I don't know very much about him, so if anybody wants to look him up and tell me more, because I don't know much about him, he was like, well, let's try this thing. Let's try to dot product B and ds. Let's try it. Let's just see what happens. This is the origins of Ampere's law, and it says right here, and this makes me, like, it validated everything in my core as I was reading this. Therefore, Ampere's law is a valid and useful principle that arose from an erroneous and abandoned work calculation. So, he was trying something. It didn't work. Like, it was not correct, right? It's bad physics, but good things came of it anyway. Okay? So, the way that I kind of look at it is that we're going to look at this interesting dot product. And we're just going to say, okay, let's look at an interesting dot product because something nice is going to come from it. So really what we're looking at, so we're looking at a magnetic field dotted with some little distance ds. So we're looking at this product for small lengths ds on a circular path around a current carrying wire. Okay. So if you're like, well, what? Let's go back to the stuff from Orsted last time. The pictures that we saw, and we saw this in real life as well, right? We had a wire with no current running through it, nothing interesting happening, all of the compasses are just pointing towards some common magnetic field. We turn current on, and by golly, whoa! These compasses are now all pointing in the direction of this new magnetic field that's being created by the wire. So we're taking chunk, 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 multiplying the magnetic field here by that little piece. That's physically what we're doing. Okay? So if we are looking at a situation like that, we know that all of the magnetic field vectors, how do they compare to the little ds's? They're all parallel, right? So all of the magnetic field vectors are parallel to the little piece ds, which is nice because then b dot ds just turns into bds, just multiplying together, right? Because if you remember a dot product is just like A dot B is just AB times the cosine of theta. Okay? So then we can we also know that the value of the magnetic field, the magnitude of it, not the direction, is constant at a given distance. Okay? And so what I want to do is to find the total for this dot product over a whole circle. Okay? So if I want to add up all of the little dS's, I'm going to use an integral. Does that make sense? I'm just going to add them all up. It's the same thing that we've always done. Now Gabe is in this little happy line integral world, and everybody else is going like, whatever, I don't even know what that is. And I mentioned this to my class last block. I was like, we're going to do line integrals. And they were like, whoa, that sounds scary. I'm like, really? Actually, no, you've been doing them forever. You just don't call them a line integral. Whenever you're adding little pieces of an actual line, that is a line integral. They just don't call it that. Maybe because they don't want to scare you. I don't know. Or because they don't want to waste their breath with that word. I don't know. But when we look around a circle, we look around a whole loop, so we're adding up all those little pieces around some loop, so we write it in a fancy way like that. Oh no, it's not scary, right?
I like it is, why does it look like a surface integral? Why are they drawn the same?
Because it's the same deal. It's the same principle, right?
Yeah.
You're summing around a surface, you're summing around a line. Like it just depends on if you're summing areas or you're summing distances. That's all.
In my multivariable top book, the surface integral had two integral signs and a little sigma.
Sometimes, yeah. No. Oh no, it's a line integral. We're just adding them up. It's really no big deal.
Just apply math.
Okay, hold on, guys. I can't hear because you're all talking too much. We're not going to talk about magnetic flux because it's not relevant yet. We'll get there. Okay? Right after break, it's all about magnetic flux. But it's not relevant for this stuff yet. So we're not going to do it. So we're just going to add up all of these little pieces, B dot ds. Why B dot ds? Because Ampere screwed up. But oh my gosh, we find out something interesting about it when we do this. Okay? So when we add up all of those little s's, and oh yeah, remember we said the strength of B was going to be the same for everything, so that's a constant so we can pull it out. So then we're really just adding up all of the little ds's. Oh yeah, but if we add up all of the little pieces around a line like we did in the last problem, you're just adding up all the little ds's, which is just going to be the circumference of the circle, right? So that's not super exciting. So really, here's the thing, is that we can write this then. So this is the magnetic field from a loop, okay? Yeah, we just did that. So this is mu naught I over 2 pi r, okay? Where r is some point, a distance, well, it's a distance r away from a wire. And then we've got ds, oh wait, well that's just going to be 2 pi r. And so then what we're saying is that this big scary thing with this circle, oh no, but it's a multiplication sign.
Okay.
Yep, I'll just leave it without. There aren't any vectors in there, so we can't, cross it up. No. So B dot ds, so a big scary thing of a line integral with a dot product in it. Oh no, really, friends? Just turns into, oh wait, there's a 2 pi r here. See ya. And there's a 2 pi r here. Oops, see ya. Is really just mu naught times I. And apparently that just, right. Put a box around that because that's important. That is Ampere's law. So this is nice, just like Gauss's law is nice, that gave us that lovely little thing that just always works. Now, this is obvious. I mean, this derivation came from just looking at a circle around a line. But the fun piece of it is, and this is where it gets more interesting, that this rule, this thing we call Ampere's law, holds for any any closed loop that surrounds a current. Any closed loop surrounding a current. So it doesn't have to be a circle. It can be a crazy funny line. It could be a box, like a rectangle. It could be a hexagon. It doesn't matter. But we can pick a convenient choice to get us where we need to go. So that's good, right? We like convenience. Okay. All right. I've got a couple of examples for you to work on. These are like just little ranking things to make sure this concept is making sense, and then we'll do a problem together to kind of put this together and really get it in our brains. All right. Oh, that's not going to work. That's a little too big for you to read or to see. Zoom out, zoom out. Okay. So this is kind of hard to see, but it was easier than setting it up a different way. Okay. So here's the situation. I'm going to kind of highlight things for you. Hopefully it'll be easier to see. I don't know why these colors are so bad. So the question asks for you to rank the magnitude of the line integral of b dot ds. Oh no! Right? For the closed paths A through D in this picture that's kind of hard to see, from greatest to least. So let me explain to you what's going on here. You don't know what's going on, do you? So right here, I don't know if you can, will you be able to see this? Can you see that? Yeah. Okay, so guys, shh, you're wasting time. And you're going to ask me what's going on, so pay attention now so that you know. There's a current carrying wire that's carrying a 1 amp current out, right here. A 5 amp current coming out of the page, right here, and a 2 amp current that's going into the page down there. Okay? There are some dotted lines here, like one right here. Is this easier to see for you?
Yeah.
Okay? This is loop C. Okay? Can you see the others okay? Or do you want me to draw them in?
You just draw them.
Sure, yeah. Here's D. That's D. This one right here is B. Oh, you want me to color code them? Jeez. Well, too bad for you. And A. Looks like this. Okay. Go. I want you to think about it, and then I'll give you a chance to talk as well. But just think about it first.
If we have a negative value, that counts as use, right? Like,
What?
Like, okay, so like, say you have like, and this is the case for this program.
Oh wait, that one's in. I didn't know. Or
So
that
you
one's
have like a negative.
yes. Oh, I didn't notice that.
Guys, can you keep your mouse or like your voices down just a little bit so I can hear? Go.
Say you have like a -6 and like they have like a 5.
A -6, like a 6 amps into the page
Yeah.
and a 5 amps out of the page. Is that what you're saying?
Yeah, you still quantify the -6 figure, right?
Yes.
Okay, cool.
The magnitude is bigger. Yes.
That's it.
Yeah, I think it's.
No, it's D. No, DC. I know what you're saying. No, actually, sorry. C is that one. C A D B. Yeah, C A D.
Oh yeah, I couldn't comment before, but Logan for today.
Change the score. That one.
Yeah.
Did you got CAD?
Oh wait, no, yeah, that's what it is. Yeah, no, I think it's
Are you ready or not quite yet?
Yeah.
Another moment?
What is the magnitude?
Approach. All right, let's talk about a better approach than flipping a coin, Teresa. So the line integral of b dot ds is equal to what?
Mu
Not I.
Okay. So the bigger that mu naught I is, the bigger that the line integral of b dot ds is. Is mu naught going to change? No. So all we really care about is, I'm going to say, the enclosed current. So did you guys do it right? Okay, so what did you say?
I don't know.
Oh.
B-A-D.
Oh, wait, are we doing from greatest to least?
Yes, greatest to least. So which one's the biggest?
C.
C. And then what?
A. G.
G.
G? D?
D.
Let's talk it through and make sure it makes sense.
Oh, no, don't get it.
So C, okay, so let's talk it through.
2 amp one's going into P.
So C is enclosing
Oh,
how
I
many?
see that.
How much current? 6. A is enclosing how much current?
5.
So it's 5 plus 1 is 6 minus 2
Or
is 4. Yay for elementary math, right?
D has -1.
D has how much?
3.
5 minus 2 is 3. And B,
-1, but that's really 1 in that.
Okay.
yeah. Are we okay?
Regardless.
Okay.
Wait, it says magnitude.
Yeah.
Right, it doesn't matter.
It still works.
Sorry.
It's -1
Yeah.
and 1. They're both less than the sign.
The rest of
It's
them.
this picture.
Yes. Oh, you want a different picture? Okay.
Oh, no.
I've got another one.
We were blaming you.
Oh, too bad. All right, here's one more. This one's a little harder to see, so listen. Shh. This one says rank the magnitudes of the line integral of b dot ds for the closed paths. I'm going to do them in color for you right now, Teresa.
Different colors?
Yes, here's A. Here's B. Here's C. And here's D. Oops, that's different. It was supposed to be gray, but it didn't work. We'll make it purple. All right, talk it out. Hey, Logan, Buck, did you guys come up with an answer back there?
Me and Nathan, we agreed on A, C, and D are all equal to the greatest.
A equals C, you said?
Yeah, equals B.
Okay.
And then those are all greater than B.
Why?
Because there's no current enclosed in B.
No current enclosed in B. So what is the value of the line integral of b dot ds for B? 0.
AC and D is 2.
What's that?
AC and D is 2.
Yeah, except you don't actually know any numbers there, friend. So I guess if you set your mu to equal some constant, yeah. Okay.
2.5.
All right. Let's try another one. This is an example. Here's the situation. This, again, is an example in both books that I was using. It's just kind of funny. It's like, oh, it's just popular. It says a wire of radius R carries a current I. Find the magnetic field inside the wire, a distance little r that's less than big R. So let's draw ourselves a wire, shall we? So here's our wire. Okay. It has a radius. So I'm going to make that a little more open so it's a little easier for us to actually. That's not good. There we go. It has a radius R. And you would agree that because it has a radius R, it's going to create a magnetic field outside the wire. Does that make sense? We did that last time. But the fun thing is that inside the wire, if it's a solid wire, and we assume that the current density is the same all the way through, we've got a magnetic field that's generated just from this part, a distance r out. Okay. So the game here is that we have to look at the current density. So current density is just how much current there is per area. Does that make sense? And I think that in your book earlier, like maybe a couple chapters ago when they were talking about current stuff, they defined current density as J. Does that sound familiar to you?
Yeah.
Okay. So current density J is equal to current divided by area. And the assumption that we have to make here is that the current density is constant throughout that wire. Okay? That it's a uniform material and that it's carrying the same amount of current per area everywhere. If that's the case, then does it make sense that the total current divided by that big area, which would be what, like pi times big R squared, would have to be equal to the current enclosed? Because now I'm just setting up a nice little line here, right, at the place that I want to look. And I want to talk about the current through that divided by the area that is actually enclosed. So that's going to be pi times little r squared. Okay. So then we can say that the enclosed current, I think in your book they say I through, but I like enclosed better. It makes more sense to me. Okay, is going to be equal to the total current times, so that's going to be what, little r squared over big R squared, because the pi's are going to go away. And if we do that, then hey, we can use Ampere's law and we can find this out pretty darn fast. Maybe, if I can get my computer to cooperate. There we go. Hey, let's do a line integral, shall we? Why not? B dot ds is equal to mu naught times the enclosed current. Right? We also know the strength of that magnetic field, or we know that this thing also, because the magnetic field is going to be the same at that place, is equal to B times D times all of those added pieces together, which is just going to be 2 pi little r. Is that okay? And now we can just plug things in together. So I can throw that thing in there. Oops, then I got rid of it. There it is. So B is equal to mu naught I total.
Can we just write I?
You can just write I if you want. I just want to make it really clear that it was the total current. R squared over big R squared divided by 2 pi r. One of those r's is going to cancel.
Why do you have to take 2 pi r into account in that case?
This one here. Is that what you're saying?
Well, yeah, because it does not cancel when you get that equation.
So yes, so the beauty of Ampere's law is that you've got this thing here, this line integral, that equals two things. You know that it equals this, but you also know that it equals the magnetic field strength times the circumference. And so in order to find out the magnetic field strength, I need to have this part too.
Yeah, okay.
Does that answer the question you're asking me? Okay. Okay. So from that, then I can write this all down, and I'm just going to rewrite this to make it a little bit prettier, to point out something lovely so that you can graph something for me here. So mu naught I over 2 pi r squared times r.
You're going to say R equals capital R, it equals the formula for the outside too?
Well, it doesn't exactly. But what I would really like you to do is to make a graph for me. That's going to take a little bit of thinking and maybe a little bit more looking back at your notes. I'm not sure. It depends on how much of it you've retained in your brain. Strength of magnetic field versus radius. I'll give you a couple of points here. I'm going to call this the radius of the circle, or the radius of the wire. And I'll give you a place here. We'll just call it the maximum. I want to know what the magnetic field does from the center of the wire to someplace outside the wire.
This
talk. Oh, go ahead.
This is just a general question.
Yeah.
So on the point that it's exactly on the very tip of the surface,
Mm-hmm.
there's still a magnetic field.
Yes.
Okay.
Yes. So, how are we doing? What is it going to look like from r equals 0 to r equals big R? It's a line with a positive slope or a negative slope? Positive slope, right? So it's going to go from 0.
You only drew positive axes.
Sometimes I do that, though, just to monkey with your head, though, right?
Maybe you do that for like little, you haven't done that to us.
Oh, I do it to the, did you say to the little kids?
Yeah.
Yeah, I do that to the little kids sometimes. And so this follows what we just found, which was B is equal to mu naught I over 2 pi big R squared times R. The maximum value that Nathan was getting at just a second ago, at big R, B max is going to have a value of mu naught I over 2 pi big R. Okay? What happens once you go outside of the wire?
Decreases with 1 over R.
1 over. And where did you get that from? We did this already, right?
Wire. In that example.
We found a wire. Didn't we do this like
Yeah,
right here?
32.3.
Yeah. This one right here, where you have a magnetic field from a wire, right? So mu naught I over 2 pi, and then this is the thing that's changing. That's your distance away from the wire. Okay? Generally, we talk about that wire being infinitely thin, but it's just an inverse deal. So we're just going to go like that. And this one is B is equal to mu naught I over 2 pi times 1 over the distance. I would not be shocked to see this on a test. I'm not saying that it is, but I know that they like to graph things and...
Yeah, the one test you gave us.
Right? I mean, there's things like... I mean, it wasn't this, but it was similar, right? It's the same idea.
On our previous
No one
test,
knows
it
how
was
to
that
joke except you.
discontinuous one where it went down, and then all of a sudden it started back up.
Yeah.
Okay. 5 minutes. Oh man, we're gonna go fast, but it's gonna be okay. You okay? Oh, maybe. So my computer decided that it was done.
All right. Good class, everyone.
Good class, except you need to know this last thing, so maybe we want to find out. All right, so
After spring break, we got it.
if you take a straight line, a line of wire, you make a magnetic field around it if you have a current, right? You take that wire and you put it into a loop. You create a magnetic field inside that loop, from that loop. Does that make sense? When we were talking about electricity, last time, that's not really last time, but when we were talking about electricity in the last kind of big concept that we were talking about, one of the things that we really wanted to do was to make a uniform electric field. How did we do that? How do we get a uniform electric field? You had to do this, right? You had to put those two parallel plates together, and then you got some uniform electric field going across. So we want the same kind of idea with a magnetic field. If you just take a magnet, the magnetic field is going to go whee like this. And so it's not going to be uniform anywhere. It didn't cross, but it's that kind of idea. Okay? If I have a loop, it's going to be the same kind of deal. So you're never going to have a constant field. But if you take a whole bunch of loops and you put them together, okay? So it's the same kind of idea that we had on this problem, where when we stacked all those wires, we found that it was pointing in this direction. If I put another loop here and another loop here and another loop here, I just keep stacking them, all of that field's going to point in the same direction. Are you with me there? And if we make the stack really, really big compared to the diameter of that loop, then oh my goodness, we can create a magnetic field, a uniform magnetic field. And what we do is we call that a solenoid. Okay? So I have a solenoid here. I'll pass it around so you can see it.
It's infinite.
Here's the deal, friends.
Oh, boy.
A solenoid is not scary, it's not weird. It's just like a spool of wire, that's it. Okay, so you just wind it around with like lots and lots and lots and lots of turns. This one doesn't say how many turns, but I would guess like on the order of thousands. Okay, it's got thousands of turns of wire. Every single turn is creating, so I have the current going this way, it's creating a magnetic field going in this direction, and they're all adding up inside here. Okay, lots and lots and lots of adding up. So I'll pass it around so you can see it. But I'm also going to look at a picture up here that kind of sketches out what the magnetic fields are going to look like. Okay? So this is not from your book, but there are similar ones in your book. So if you look at one loop, it's just going to have those loops like that, but then when you squish them all together, inside here, you're going to have a strong magnetic field that's uniform. And outside, what actually happens is that the magnetic field outside is very, very weak relative to the inside. This is an electromagnet. Okay? When people talk about an electromagnet, friends, it's just a coil of wire and you put a current through it. That's it. There's nothing else big or scary about it. Okay? That's what's going on. Are we good so far?
Say that, can you guys one more time? I was looking at it.
Which part?
Just everything you just said about the pictures.
No, because I don't remember what it was, and we only have 3 minutes.
I get it. I don't
All right, so we're going to go fast. So ladies and gentlemen, I need to listen really, really carefully for just a couple of more minutes, okay? So the game here is that we not only want to create this uniform magnetic field, we also want to be able to figure out how big it is. Okay? So in order to do that, well, we'll do this in a second, but I'm just going to write things down here. We know that in a solenoid, okay, the magnetic fields inside are going to reinforce one another. It's a vector, so they're just going to add, okay? And outside, what actually happens, unlike the picture that you saw before, they actually end up canceling each other out. B field is nearly zero, yep. Okay. Because, here, let me go back to this picture again. You've got some that's pushing this way, and you've got some from up here that's pushing the other way, and so they cancel each other. There's a really nice picture in your book. I'm just trying to go fast because we only have like a minute left. But if you look on page, I'll tell you, no, I'm not going to find it. 938, it will tell you. It has a really nice picture. Figure 3230. Okay? An ideal solenoid, the ones that we really, really care about that are going to give us the best uniform magnetic fields, I just mentioned this before, have a length that is much, much greater than the diameter. And it's time to go, and so we'll calculate the magnetic field next time.
Wait, can you go back to that last thing that you had?
The last page?
It's like outside B field nearly zero, and that's all I got.
Yes. There you go. All right, we'll finish this up next time.
Did I say B dot S?
Because the magnetic fields cancel each other out.